This is Jack Jackson. We're going to continue to look at compositions of reflections. This one, we're going to look at composition of two reflections. Just to remind you, last time we looked at uh, two reflections where the second line was the same as the first line. And there we saw we got an intermediate image, but the final image was the same as the original, so we got the identity transformation. When it was a parallel line, we would get the first image over here, and then the second image is over here. It turns out that that one turns out to be a translation, as you can see there. And specifically, this vector is twice uh, the distance between the two lines, and it's in the same direction as from the first line to the second one, perpendicular to both mirror lines, and the distance is twice as far. So we made those conclusions last time, and this time what we're going to do is we're going to look at what happens when it's a mirror image about two lines, but this time the two lines are going to intersect. Okay, so here we have a pre-image and a first image. When we reflect over the blue line, the first mirror, we get A prime B, A double, or A prime B prime C prime. Reflect that over the second line to get the second image. Can you see what occurs this time? Is it a translation, reflection, rotation, cloud reflection? What is it? Well, maybe you can see that it is actually um, one way to help us see this is to look at the line segments that connect up pre-image to image point, and notice that they're not parallel. They're not necessarily the same length. Their midpoints are not necessarily in the same line. But if we look at these perpendicular bisectors of these line segments, they all intersect at back where the two lines originally crossed. Ah, well, that's going to tell us that the result is actually a rotation. Okay, since these line segments, perpendicular bisectors of these line segments from here to here. So if let's just get rid of the first image and just compare these two. Again, how do we get from the blue to the red in one step? Well, we see that these are perpendicular bisectors go through that one there, and that's going to give us a rotation. These have to be the same length because um, the perpendicular bisector is equally distant for both of these pre-image and final image points. Um, so how do we go about actually proving this? It's a little bit challenging here uh, because of the different cases that we come up with. So the first case, um, so let's look at this. By definition, the um, perpendicular bisectors, when we do these, okay, so when we do this first image, from here to here, the perpendicular bisector of this, well, let's put it this way. This point that that's on this first mirror line, it's going to be go through the midpoint of the line segment from A to A prime. So A and A prime are equally distant from X. Well, A prime and A double prime are also equally distant from X or Z, this point of intersection, because of this being a perpendicular bisector of the line segment going from here to here. So looking at this line segment, that's going to be perpendicularly bisected as well. So that tells us that A prime, and A double prime are all equally distant from this center point. Okay. So that's our first thing. By definition, mirror lines are perpendicular bisectors of line segments A to A prime, line segment A prime to A double prime. As well, by an earlier proposition, we know the intersection of the two mirror lines is the circumcenter of triangle A prime, A double prime, or the perpendicular bisector theorem. So we know that AZ, the distance from A to Z, is the same as the distance from A prime to Z, and is the distance the same as A double prime to Z. So the final image is the same distance for Z as its pre-image. We can go ahead and put in that A prime Z is that same length. Okay, that's going to be for good. We're going to let M be the midpoint of the distance from A to A prime. So here it's going to be the midpoint of this one. We're going to call that guy M. We're just going to caption that as M. And where this one crosses here, we're going to capture that one, caption that as N. So we're going to give those things names. So we're talking, so we know what these 2 points are. Now, that's not what I want. Sorry, that's not N. Yeah, this one that I've got is X here. I'm going to now call that one N. M. That's the first midpoint. And then from here to here, this one is N. That's how I want it to be. Okay, so let's now at this point, then the angle here from between N to Z to M is the angle between these, at least one of the 2 angles between these lines. And then we want to also look at the angle from A to Z to A double prime. Turns out it's going to be a rotation, and it turns out this amount here is going to be half of this smaller angle here. Or, I'm sorry, it's going to, this angle is going to be twice that. Or if we go twice of this angle here, that will be a rotation around the longer way. Okay. So there are several cases to consider here depending on the placement. This is where it starts getting a little technical. So I've got pictures of each of these. Let me zoom in a bit. So we've got a few subcases to look at. Now, we're going to have the distance, if we draw the line segments from this center point here, which I'm calling Z, and if I connect it to A prime and A double prime, those green line segments are all the same length. They're radii of this circle here, which is circumscribing this triangle that you see here. Okay, now we've got some isosceles triangles going on because of the different pairs of green sides that we can look at. So in particular, we know that the measure of angle A prime ZA, so that's going to be here to here to here, that's going to be twice this angle, say from A, well, the angle from A to Z to M is the same size as the angle from A prime to Z to M. Okay, so if you go A prime to Z to A, that big angle is going to be twice the angle from the midpoint M to Z to A. And similarly, you're going to get the same relationship for this isosceles triangle over here. This going through the midpoint is going to be a perpendicular bisector of this side. And it's a bisector of this angle as well. So this angle from A prime to Z to A double prime, or here it is going to have twice the measure of the angle from N to Z to, say, A prime. Now we've got several cases at this point. So those things are in general. So it could be that A and A double prime, when it's all said and done, are both in the interior of the angle MZN. So let's look at MZN. Here is M. Where's M? MZN. And if they're both in the interior. Okay, so our first case is we look at the angle MNZ. Here's M, or MZN. Here's the angle right here, which is an angle between the two lines, right? And we assume that both A and A double prime are in the exterior of that angle, which is what we have in the picture here. Okay, so let's look at this a little carefully. So start with measure of A, Z, A prime. Okay. Okay, we want the AZ, A double prime. A, Z, A double prime here. Okay, we want that angle. We want to see how big that is. Okay, now we know that we have a bunch of isosceles triangles here. So if we look at, so you can see in orange, this angle here, okay, 91 degrees or so, okay. We take the measure of AZ, A prime. Where is that? That's A, Z, A prime. That's going to be, we take that measure plus the measure from A prime Z to A double prime. Together, those are going to give us the measure of the angle from A all the way around here to A double prime. Okay, because of the order of these rays here. Okay, but the measure of AZ A prime is going to be twice the measure of MZ uh, MZ MZA. Okay, MZA, twice that one. And this one, because this isosceles triangle thing over here, this bisects the angle there as well. So that's going to be twice the measure of AZN. Now we have two 2's here, so we factor that out. This is going to give us the measure of AZX, AZN, M, and then this gives us AZN. No. Okay, I've got this now, I think, fixed. So let's start over. We got the measure from AZ to A double prime. A to Z to A double prime. In this case, it's going around this way. Is going to be the measure from AZ to A prime plus the measure from A prime Z to A double prime. Okay, that's what I want to say. Now this angle here is actually twice the angle just from M to Z to A prime. So this one is twice that one. And then again by this isosceles triangle theorem both times, this angle here from A prime to Z to A double prime is twice the angle from A prime to Z to N. We have the two 2's, we factor that out, and when you add these two angles here together, you get the angle from M to Z to N, which is the angle between the two. So the angle from A all the way to A prime is actually twice the measure of the angle here. Okay, that's what we want to show happens every time. So we've got it. This is actually the easiest case. Now the next case here, we want A to be in the interior of MZN. Let's see if our picture's right. So MZN, A is in the interior of that angle. You can see that. And then A prime is in the exterior. So it's out here somewhere. A double prime is. So once again, we still got this isosceles triangle theorem going. So the measure of AZ to A double prime, which is what we want to find, AZ to A double prime, that angle there. We want to find that angle. Okay, so let's look at the picture for it to help us out with the betweenness relationships here. We can find that as adding A prime, A double prime Z to N plus the angle from A Z to N. Okay, so that angle and that angle add up to that one. Okay, that's cool. But we also want to look at this how we go from there. Okay. Okay, so now A prime Zn, A double prime Zn from here to here is the same as A prime Zn. So I can replace that with that one. Now what about this A to Z to N? That's this one right here. It's a little harder to see what's going on here. A to Z to N. Okay, well look at this bigger angle. A prime Z to N. Okay, we can take that one and subtract the angle A prime ZA. Okay, now notice these two are the same. We can add those up. But this A prime ZA is twice the angle from M to A, M to Z to M, M to Z to A, or AZM. Well, now we see the two 2's. We can factor that out. This gives us AZN, measure that, minus the measure from AZM. Okay. A to Z to N minus the measure from A to Z to M. Let me say it again. A prime to Z to N minus A to Z to M, which is the same as A prime ZM. Let me write it that way instead. And that is the measure from M to Z to N. We still have the 2, so we get twice the angle that we want. Okay, so that's case B, subcase B. Subcase C is very similar. This time A prime is on, A double prime is in the interior, A is in the exterior. We're just going to reverse the roles of A and A double prime and reverse the roles of M and N. So we're finding the measure of A, Z, A double prime. A, Z, A double prime. Well, first of all, look at the picture. Here's our M to Z to N. Where's N? N is right there. N is that one. Yes. That one right there is N. This one is M. No. This one is M right here. N right here. This is M. So here's M to Z to N. A double prime is in the interior. A prime, A, the original A is in the exterior. Okay, that's what we want. So we take A to Z to A double prime, A to Z to A double prime here. That's from here to here to here. Isosceles triangle again, bisected by the mirror line, the original one, the blue one here. Okay, that's the angle we want to know. Actually, we want to know what angle that is. It's not necessarily bisected by that one. Okay, so let's see what we've got. A prime to Z to M. So it's A prime to Z to the midpoint here. Plus A double prime to Z to M. Double prime to Z to M. A prime to Z to M plus M A double prime to Z to M. Okay, let me say this better. We're finding the distance, the angle from A, Z to A double prime. A, Z, A double prime. We can get that by adding the angle A, Z to M plus the angle from M, Z to A double prime. So we're getting the angle here by getting the angle here plus the angle here. Okay, that's what this says. AZM plus the measure of angle A double prime ZM gives us from AZ to A double prime. That's right. Okay, but this angle from AZM is the same size as the angle A prime ZM. So I can replace that one with that. A prime double prime ZM, okay, is the distance is A prime ZM minus A prime Z A double prime. Now those two are the same, so that doubles up. But this angle A prime Z A double prime is twice this angle from N to Z to A double prime. Right? That's what I have here. Factor out the 2. That should have a double prime. So now we go A prime to Z to M. A prime to Z to M minus a double prime to Z to M okay, I think I want to say it this way. So this angle from A prime Z to A double prime is twice the angle from A prime to Z to N. Okay, let's say it that way. Factor that out. Now, if we take A prime to Z to M, A prime to Z to M, and we subtract off A prime to Z to N, you are left with the angle from M to Z to N. Right, that's what we want. And so we got the 2 there, so that works out to be twice the angle. It's a little tricky to get all these angles exactly in the right place and just keep track of all of it. The only other case that you think might exist is that both A and A prime are in the interior of angle MZN, but that's actually not possible. If A prime's on the opposite side of the first mirror line from A, and A double prime's on the opposite side of the mirror 2 from A prime, however, since A prime's in the interior of angle MZN, A's on the same side of M2 as A prime just cannot be on the same side of M2 as A prime, therefore they cannot both be in the interior of that angle. So we see the only cases that can actually occur A, B, and C. And In all cases, what do we see? The measure from the angle from A to Z to A double prime, from the pre-image to the center to the final image, is twice the measure of the angle, that is from M to Z to N. That's the original angle between the two lines. So the result is ultimately a single rotation about the intersection of the two mirror lines by amount equal to twice the measure of the smallest positive rotation from the first mirror line to the second mirror line. One example we've already seen of this is a rotation of 180 degrees about a center point can be viewed as the composition of two reflections, one about any line through the center point and the other about another mirror line through the center point perpendicular to the first mirror line. For example, the one we looked at specifically was rotating 100 degrees about the origin can be viewed as a reflection about the x-axis followed by a reflection about the y-axis. This generalizes that result so that anytime you have two intersecting lines, you're going to end up with, and you're going to reflect about both of those, then you end up with the equivalent of one single reflection about the center being the intersection of the two lines and the angle being twice the angle between the two. We'll look at three reflections then a little bit later.